Welcome to Spaceverse, your portal to cosmic adventures. Charon, Pluto's largest moon, is often overshadowed by its parent dwarf planet. But deep in the Kuiper Belt, where icy relics of the early solar system linger in the cold and dark, Charon has been hiding something astonishing. Something it's only just now revealing, thanks to the most powerful space telescope ever built. Astronomers using the James Webb Space Telescope, or JWST, have made a groundbreaking discovery. Carbon dioxide and hydrogen peroxide have been detected on Charon's frozen surface for the very first time. These are more than just molecules, they're cosmic clues to how this icy world and others like it were formed. Let's go back in time for a moment. Charon was discovered in 1978. Since then, scientists have been eager to understand what it's made of. Over the decades, researchers have identified water ice, ammonia-bearing compounds, and organic molecules on Charon's surface. But there's been a lingering mystery. Previous observations simply didn't have the capability to explore Charon in the infrared wavelengths where many key molecules leave their spectral fingerprints. That limitation left a major gap in our understanding until now. Enter the James Webb Space Telescope and its powerful near-infrared spectrograph, or NIRSpec. This is the same instrument that has been peering into the hearts of distant galaxies, examining exoplanet atmospheres, and now it has turned its eyes to Charon. The team behind this discovery was led by Silvia Protopapa of the Southwest Research Institute. She and her colleagues used JWST's NIRSpec to study Charon in the infrared with unprecedented sensitivity. The results were stunning. Protopapa explained, "Our research reveals that Charon's surface preserves evidence of its formation through the presence of carbon dioxide, as well as signs of irradiation processes, indicated by the presence of hydrogen peroxide. This is huge. These two newly detected molecules expand Charon's known chemical inventory, which already includes water ice, ammonia-bearing species, and the organic materials that give the moon its gray and red coloration." Let's take a step back and look at the context of where Charon resides. Charon is a mid-sized celestial body about 750 miles or 1,207 kilometers wide. It orbits Pluto within the Kuiper Belt, a vast ring of icy debris, comets, and dwarf planets at the edge of the solar system. These are what we call trans-Neptunian objects, or TNOs. What makes Charon so important, though, is its bare surface. Unlike many larger Kuiper Belt objects, Charon's surface isn't buried under volatile ices like methane. That gives scientists a rare, clear view of how surfaces in the outer solar system evolve, how sunlight, cosmic rays, and geological processes leave their marks over billions of years. On top of that, Charon is the only mid-sized TNO that has been geologically mapped. And we have the New Horizons spacecraft to thank for that. When it visited the Pluto system in 2015, it gave us our first close-up look at Charon's terrain, impact craters, smooth plains, and even hints of tectonic activity. Overall, Protopapa noted, these factors make Charon an invaluable target from which we can learn extensively. Our findings provide valuable insights into how processes such as sunlight exposure and cratering shape the surface of Charon, and by extension, other mid-sized icy bodies beyond Neptune's orbit. Let's talk about the science behind these detections. When scientists study the composition of distant planets and moons, they use a technique called spectroscopy. Light, when passed through a prism or a spectrometer, splits into a spectrum of colors. But elements and molecules absorb and emit light at specific wavelengths, like fingerprints in light. By analyzing these patterns, scientists can figure out exactly what a celestial object is made of. Protopapa and her team took the spectra from JWST's observations of Charon and compared them with lab data and models. What they found was crystal clear. Carbon dioxide was present on Charon's surface. Not just anywhere either. The data suggests that CO2 is concentrated on the surface as a thin veneer sitting atop a subsurface rich in water ice. According to Protopapa, the surface of Charon, as revealed by the New Horizons mission, features numerous craters surrounded by bright ejecta blankets that are rich in water ice and ammonia-bearing compounds. These geologic features suggest that materials from beneath the surface have been exposed by impact events, providing a window into the moon's subsurface composition. That's right, cratering events act like cosmic shovels, digging through Charon's crust and tossing up material from deeper within. That's likely how the carbon dioxide reached the surface. And here's the kicker. Scientists always expected CO2 to be there. Based on theories about the protoplanetary disk from which Pluto and Charon formed, carbon dioxide should have been incorporated into the early building blocks of the system. But the New Horizons spacecraft didn't detect it in 2015, which puzzled scientists for years. So when JWST finally confirmed its presence, the detection of carbon dioxide was a satisfying confirmation of our expectations, said Protopapa. But not everything went according to expectation. What truly stunned the team was the detection of hydrogen peroxide. I honestly did not expect to find evidence of it on the surface, Protopapa admitted. Hydrogen peroxide has been known to be present on Jupiter's moon Europa's surface since the 2000s. I never imagined I would be writing a paper comparing these icy satellites, Charon and Europa, given how different their environments are. It's true. Europa is bombarded by radiation from Jupiter's immense magnetic field. That radiation helps produce hydrogen peroxide through chemical interactions with surface ice. But Charon? It's way out at the edge of the solar system, where sunlight is 1,000 times weaker than it is on Earth, and intense magnetic fields are non-existent. So how is hydrogen peroxide forming on Charon? The team believes it's the result of irradiation by ultraviolet light, solar wind particles, and even galactic cosmic rays. These sources can break apart water molecules, creating highly reactive hydroxide ion radicals. When two of these radicals come together, they form hydrogen peroxide. Protopapa explained, hydrogen peroxide forms from the combination of neighboring hydroxide ion radicals, which originate from the breakup of water molecules due to incoming ions, electrons, or photons. To back up this theory, the researchers even conducted new laboratory experiments to test if hydrogen peroxide could still form in the presence of carbon dioxide. And sure enough, it worked. So not only do we now know that Charon has carbon dioxide from its interior, we also know that its surface is being actively altered by cosmic radiation. And this isn't just about Charon. These discoveries tell us something much larger about the dynamics of icy worlds throughout the solar system, and even beyond. But the journey's not over yet. According to Protopapa, this is just the beginning. The James Webb Space Telescope will continue to observe Charon, targeting spectral gaps not covered in the current data. Future JWST observations, targeting the spectral gaps not covered in the current data, could lead to new Charon discoveries and further expand its chemical inventory, possibly revealing other mechanisms at play, she said. Every new molecule detected adds another piece to the puzzle of Charon's history, and by extension, the history of the outer solar system. We're not just learning about one moon. We're uncovering the cosmic story of how icy bodies evolve, how they interact with their environment, and how radiation, light, and chemistry come together in places so far from the sun they were once considered too quiet, too distant to matter. But now, with the eyes of the James Webb Space Telescope, even these faraway worlds are speaking. And we're finally starting to understand what they're saying. Charon's icy secrets are only beginning to surface, and the universe has so much more to tell us. If you enjoyed uncovering these cosmic clues with us, don't forget to like, subscribe, and tap that notification bell so you never miss a journey to the edges of the solar system. This is Spaceverse, where every pixel from deep space brings us closer to the truth. Keep looking up.